Okay, here we are, lesson 23 from Unit 4, the defining equation of a line. So what you're going to need is graph paper. And we're going to start with the exploratory challenge, which is the lesson worksheet, but you're also going to need your graph paper. So complete number 1 on graph paper. Sketch the graph of the equation 9x plus 3y equals 18 using intercepts. When you've done this, continue the video. Alright, so if you figure out the intercepts, remember that to figure out the y-intercept, we would replace x with 0, and you would get y equals 6, and so your y-intercept is 0, 6, and then when you plug in 0 for y, you would get x equals 2, so the x-intercept is 2 and 0. So when you graph this, you would get a graph that should look like this. Alright, so now sketch the graph of the equation y equals negative 3x plus 6 on the same coordinate plane. When you've done this, go ahead and continue the video. Alright, you should be done graphing. So what do you notice about the graphs of 9x plus 3y equals 18 and y equals negative 3x plus 6? Why do you think this is so? Well, the graphs of the equations produce the same line. Both equations go through the same 2 points, so they are the same line. So rewrite y equals negative 3x plus 6 in standard form. Well, we would start with 3x plus y equals 6 by adding 3x to both sides, and identify the constants a, b, and c of the equation in standard form from part C. Well, that would be a equals 3, b equals 1, and c equals 6. So now identify the constants of the equation 9x plus 3y equals 18, and note them as a prime, b prime, and c prime. Well, you'd have a prime is 9, b prime is 3, and c prime is 18. So what do you notice about the relationship or the ratio between a prime to a, b prime to b, and c prime to c? Well, a prime to a is 9 to 3, which is 3. B prime to b is 3 to 1, which is 3. And c prime to c is 18 over 6, which is 3. So each fraction is equal to the number 3. Alright, for number 2, sketch the graph of the equation y equals 1/2 x plus 3 using the y-intercept and slope. Continue the video when you are done. Alright, so now once you've got that graph, sketch the graph of the equation 4x minus 8y equals negative 24 using intercepts on the same coordinate plane. Go ahead and continue the video when you are done. Well, to figure out the y-intercept, you would have gotten y is 3, so the y-intercept is 0, 3. And by replacing y with 0, you would have figured the x-intercept to be at negative 6, so the x-intercept is negative 6, 0. And your graph should look like this. So what do you notice about the graphs of y equals 1/2 x plus 3 and 4x minus 8y equals negative 24? And why do you think this is so? Well, the graphs of the equations produce the same line. Both equations go through the same 2 points, so they are the same line. So rewrite y equals 1/2 x plus 3 in standard form. Well, we can cancel out or effectively get rid of the fraction by multiplying the whole equation by 2. That would mean 2y equals x plus 6. And then when we write it in standard form, we have to subtract x from both sides. So that gives us a negative x plus 2y equals 6. But we really don't want to have a negative x, so again, multiply the whole entire equation by negative 1, and we get our standard form, x minus 2y equals negative 6. So identify the constants a, b, and c of the equation in standard form from part C. Well, a is 1, b is negative 2, and c is negative 6. So identify the constants of the equation 4x minus 8y equals negative 24 and note them as a prime, b prime, and c prime. Well, a prime is 4, b prime is negative 8, and c prime is negative 24. So what do you notice about the relationship between a prime to a, b prime to b, and c prime to c? Well, a prime to a is 4 to 1, which is 4. B prime to b is negative 8 over negative 2, which is 4. And c prime to c is negative 24 to negative 6, which is also 4. So each fraction is equal to the number 4. All right, number 3. The graphs of equations y equals 2/3 x minus 4 and 6x minus 9y equals 36 are the same line. So rewrite y equals 2/3 x minus 4 in standard form. Well, again, when we effectively get rid of the fraction by multiplying the whole equation by 3, we end up with 3y equals 2x minus 12. Then by subtracting 2x from both sides of the equation, we get negative 2x plus 3y equals negative 12. And so in order to end up with a positive x, multiply the whole equation by negative 1, and that gives us 2x minus 3y equals 12. So again, identify the constants a, b, and c of the equation in standard form from part A. Well, that would be a equals 2, b equals negative 3, and c equals 12. And identify the constants of the equation 6x minus 9y equals 36. Note them as a prime, b prime, and c prime. A prime is 6, b prime is negative 9, and c prime is 36. So what do you notice about the relationship between a prime and a, b prime and b, and c prime and c? Well, a prime to a is 6 to 2, which is 3. B prime to b is negative 9 to negative 3, which is 3. And c prime to c is 36 to 12, which is 3. So each fraction is equal to the number 3. So you should have noticed that each fraction was equal to the same constant. Multiply the constant by the standard form of the equation from part A, and what do you notice? Well, 2x minus 3y equals 12 can be multiplied by 3, which makes it 6x minus 9y equals 36. So after multiplying the equation from part A by 3, you should have noticed that it is the exact same equation that was given. So let's go ahead and take a look at a theorem and discuss it. You're going to need to take notes in your journal and again try to synthesize this as much as possible. So what do you notice about the equations you graphed in each of the exercises 1, 2, and 3? Well, in each case, the graphs of the equations are the same line. So what you observed in exercises 1 through 3 can be summarized in the following theorem. Suppose A, B, C, A prime, B prime, and C prime are all constants, where at least one of A or B is non-zero, and one of A prime or B prime is also non-zero. For part 1, if there is a non-zero number s, so that a prime is equal to s times a, b prime is equal to s times b, and c prime is equal to s times c, then the graphs of the equations ax plus by equals c and a prime x plus b prime y equals c prime are the same line. And the second part, or counter example of that, would be if the graphs of the equations ax plus by equals c and a prime x plus b prime x equals c prime are the same line, then there exists a non-zero number s so that a prime is equal to s times a, b prime is equal to s times b, and c prime is equal to s times c. If you go back and think about dilations, you might recognize that s is the same as a dilation factor. So we want to show that 1 is true. We need to show that the graphs of the equations ax plus by equals c and a prime x plus b prime y equals c prime are the same. So what information are we given in part 1 that will be useful in showing that the two equations are the same? Well, we are given that a prime is equal to s times a, b prime is equal to s times b, and c prime is equal to s times c. We can use substitution in the equation a prime x plus b prime y equals c prime, since we know that a prime, b prime, and c prime are all equal to s. So then by substitution we have a prime x plus b prime y equals c prime, which means we can replace the a prime with s times a, the b prime with s times b, and the c prime with just sc. So now by the distributive property we can factor out the s, but we're only going to do that on the left side of the equation. So if we factor out the s, we are left with s times the quantity of ax plus by. Well, I'll divide both sides of the equation by s so that we can effectively get rid of it, and we end up with ax plus by equals c, which means the graph of a prime x plus b prime y equals c prime is equal to the graph of ax plus by equals c. That is, they represent the same line, therefore we have proved part 1. So now let's move to proving part 2. We will assume that a and b is not equal to 0. That is, we're not dealing with horizontal or vertical lines. Proving 2 will require us to rewrite the given equations ax plus by equals c and a prime x plus b prime y equals c prime in slope-intercept form. So let's rewrite the equations. First of all, we're going to subtract ax from both sides, and when we do that, then we end up dividing by b so that we get y is equal to negative a over b times x plus c over b. When we do the same thing to a prime x prime plus b prime, a prime x plus b prime y equals c prime, we end up with the same thing. So we subtract the a prime x from both sides and then divide by b to isolate the y. So we're going to refer to our first slope-intercept equation as a and our second slope-intercept equation with the primes in it as b. So what are the slopes of a and b? Well, the slope of a is negative a over b, and the slope of b is negative a prime over b prime. Since we know that two lines are the same, we know the slopes must be the same. So negative a over b is equal to negative a prime over b prime. When we multiply both sides of the equation by negative 1, we have a over b equals a prime over b prime. So by the multiplication property of equality, we can write a over b equals a prime over b prime as, and follow through this because this is a little tricky, but it actually will change the order of the proportion. So a over b equals a prime over b prime. When we cross multiply or use cross products, we would get a times b prime equals a prime times b. So now what we're going to do is divide or multiply by 1 over a times b. And we're going to do this to both sides. When we do this, and again this is our multiplication property of equality, we end up with a b prime over a b, which we can split up into two separate fractions on each side. This is our cross product formula, which means if I have a b prime over a b and a prime b over a b, I can write them as two separate fractions. A over a times b prime over b equals a prime over a times b over b. So essentially, because the identity property of multiplication, a over a equals 1, and therefore 1 times any number, value, or variable is going to be the same thing, we end up now with b prime over b equals a prime over a. So a over b is equal to a prime over b prime is equivalent to, and notice the change in order, now a prime is over a and b prime is over b. This is not a sleight of hand. Remember that as we move down, all of these are equivalent to each other, which means we haven't changed the truth of the equation. So by using the properties, we have effectively moved the variables around and created still a true equation. But let's look at this a little bit more, since it's kind of hard to see it with the variables. So let's do it with some numbers so that you can see that this is not a trick. If we have 1/2 is equal to 5/10, and I use cross products, 1 times 10 is still 10, and 2 times 5 is still 10. So we still have a true equation. So now let's say that I multiply both sides, 1 times 10, by 1 over 1 times 2. I'm using, where I'm getting my numbers are the digits or the values that are in the equation. I still have a true statement. So this is the multiplication property of equality. So now what I have is I would have 1 times 10 over 1 times 2, and because of our product formula, which we mentioned in the previous example, this can be split up as to 1 over 1 times 10 over 2 and 2 over 2 times 10 or 5 over 1. If you were to multiply these out, remember this is still true. This would still be 10 over 2 is equal to 10 over 2. So now, since 1 over 1 is 1, that effectively sends that away. We still are left with 10 over 2, and the 2 over 2 is 1, so we're left with 5 over 1. Well, 10 halves is the same as 5 over 1. But notice what has happened. 1/2 is equal to 5/10, but also 10 halves is equal to 5 over 1. So even though 1/2 is equal to 1/2, this has changed. 10 over 2 is 5, and 5 over 1 is 5. So, but we don't have the same value, but we still have a true equation. So that's what we're looking for. And that is the identity property of multiplication. So, and keeping in mind that when we have proportions, we also have an equivalent proportion. We could write this as 1/5 is equal to 2/10. Notice how we still have the same values, 1, 2, 5, and 10. We have 1, 2, 5, and 10 in a different order, and we have 1, 2, 5, and 10 in a third order. So when we work with proportions, there's really 3 orders of the 4 numbers that would still, if you change the order of them and the placement, will still provide a true proportion or equation. All right, so another way to accomplish this is using the properties is, let's say we have a over b equals a prime over b prime. Well, by using cross products, again, we get a times b prime equals b times a prime. And we can flip this around by using the commutative property of multiplication. So b prime times a is equal to b times a prime, leaving the right side alone. And when we use cross products to put it back in order, so if b times a would be b times a here, b times a would be b times a here, notice that we've switched the order around. So now a over b is now b prime over b, and a prime over b prime is now a prime over a. So let's go back to our proof now that we have digressed a little bit to show how we can manipulate proportions. Now what is the y-intercepts? So the y of these equations, y equals negative ab times x plus cb for a, and y equals negative a prime over b prime times x plus c prime over b prime. Well, the y-intercept would be c over b, and the y-intercept of equation b would be c prime over b prime. Well, because we know that the two lines are the same, the y-intercepts will have to be the same. So c over b is equal to c prime over b prime. So we can rewrite the proportion. C prime over c is equal to b prime over b. So again, go back to the previous discussion we just had. We're not even going to prove it, we'll just go ahead and rewrite it. So now, using the transitive property and the fact that a prime over a is equal to b prime over b, and we said that c prime over c is equal to b prime over b, which just came from up here, we can make the following statement. That a prime over a is equal to b prime over b is equal to c prime over c. Therefore, all three ratios are equal to the same number, so let's call that same number s. So therefore, a prime over a is equal to s, b prime over b is equal to s, and c prime over c is equal to s. So now we can rewrite this to state that a prime is equal to s times a, b prime is equal to s times b, and c prime is equal to s times c, which is just what we said in part 2 of our theorem. Therefore, we've proved it. So when two equations are the same, for example, their graphs are the same line, we say that any one of those equations is the defining equation of the line. All right, go ahead and complete exercises 4 through 8 and be prepared to share your answers in class. And to wrap up, we know that when the graphs of two equations are the same line, it is because they are the same equation in different forms. We know that even if the equations with the same line as their graph look different, i.e. different constants or different forms, that any one of those equations can be referred to as the defining equation of the line. All right, we'll see you in class.